control of soft robots. But before that, a bit about what we're working on. We're working on using micro needle sized robots for age-related macular degeneration, which is a case that degenerates the retina in elderly people. We developed these concentric tube robots. We try to model their dynamics, solve the planning, and also develop virtual reality environment for training of users. This is the kind of robot that we're working on. Tube robots are basically multi-use event structure, and as a result of twisting and moving next to each other, we get the stable motions called snapping as
Sorry, I'm having a little trouble hearing you on the virtual end. It might just be me.
What about now?
That's perfect, thanks. Sorry for the interruption.
Okay, I have to just keep it closer. We're working on complex multi-arm concentric tube robots. You kind of see the actual size with respect to a replica of human eye with multiple arms holding a needle, a gripper, and a camera. And also performing ex vivo tests with realistic phantoms made of silicon and also porcine eye samples. We also do a bit of growing robotics. Properly placed for mammography. The robot is consisting of a growing sheath on top of a tendon-driven catheter for steering, and the sheath provides friction-free sliding in narrow duct, like mammary duct in this case, while the steerable catheter used for steering and liaising with the sheath grows. That's the kind of things that we are doing at our lab, but now about the modeling, which is the backbone of our work. I started dealing with the modeling challenges and design gave very headache. So fast dynamics, 3D motion, complex sense, external load, all really challenging to capture. I started with kind of categorizing what has been done at the community, because usually the papers started talking about their method instead of providing a structure that helps with making that method comparable. I break the model for a continuum robot, which is, well, in continuum robotics community, that's trivial. In soft robotics, so a model should have a kinematics, a system mechanics, conservation of law, and material mechanics, constitutional law. And I categorize the different kinematics and system mechanics and also material mechanics being used at the time. Also the formulations, strong formulations, weak formulations, and finally the solutions for that that identified as forward and indirect. So this categorization kind of helped me to see what is what, how people are approaching the modeling, how we can combine these elements to get a better model. And that's the beginning of TMTDyn, because TMTDyn is not about making a simulation fast for you or giving you a lot of elements or a lot of soft robots to interact with each other, but it's about implementing theory and comparing different methods in the community and going for modeling systems that there is not a model for, and I'm going to discuss that a bit. These are some of the research covered in the community on these modeling methods, but the journey starts with me trying to model precisely the cross-section deformation of the stiff flop as it bent, and as you can see, it could become a weird egg shape as a result of bending. There were in one paper we compared all of the methods to the point for capturing this asymmetric deformation, improving one based on the problem of flexure, a very old work, improving it, and could capture that weird egg shape. Well, of course, we published it, then looked into the braid, the modeling for the braids, how the braids can be modeled. There were methods for mat-given muscles around. I utilized them, but then I tried to implement it as simple as possible and came up with simplifying assumptions and provide comparison to show how simple you can get it. But then I noted that, who cares? The cross-section deformation, it improves 3% of accuracy in our cases, and the braided actuators, well, these models are good, but most of the people don't care about the cross-section and inhomogeneity in the structure. So I looked into the backbone model. We can discretize them as series links, as Euler-Bernoulli beams with strains and torsion as states, or as Euler-Bernoulli beams in between lumped masses with known states, position and orientation in space. In a sense, if you go for strains as a state, you're doing kinematics like rigid body dynamics. But if you do absolute states, absolute orientation position as a state, you're doing finite element modeling. Then I explored reduced order modeling, basically fitting a known shape function either to the geometry, the backbone shape, or the strain and shear and bending. I noted that getting the tangent frame and the real material frame, enforcing that by the constitutional law is not accurate enough. So recently we developed a specific bishop frame to guarantee that tangency and the correctness of capturing the material frame. And recently, Federico Render's team have developed a similar method, but instead of capturing the system geometry, they went for capturing the strains and torsion with these reduced order models. And as I said, if you assume relative states in your model, you're doing the rigid body dynamics, but if you assume absolute states, you're kind of doing finite element modeling. And this category kind of shows if you choose the reduced order modeling path, how these models will be similar to the traditional finite element and rigid body kinematics model. But what I like about my work is I like beautiful, concise derivation. So you see a lot of derivations in the paper, simplifications, etc. But this is actually the equations behind all of the models that I presented. Just rotations of quaternions, Kossrat kinematics, rigid body dynamics in three forms, with Lie algebra, with basically Bishop-like discretization, or with Euler-Bernoulli angle, forward map and inverse map of the Kossrat model, and also their discretized version, reduced order modeling by fitting a polynomial to the backbone shape and considering that a specific Bishop frame that guarantees tangency of the local frame to the backbone of the robot. Our paper, 2020 paper, was basically presenting these derivations, providing a comparison and implementing all of them in the TMTDyn. So you get the chance to see the comparison there. But then the dynamics, we could do Lagrangian at the time, and we could do principal of virtual work, but I knew TMTDyn, which helped simplifying the steps required to get the closed vector form for the equation of motion. in the if you go the Lagrangian route, you need to do the spatial partial derivations, and you end up with a complex relation that you need to collect the terms and put it in the linear form. Or you need to do finite element modeling, and you already know that the system is decoupled and generate these vector formalism from the beginning. But if you go for a rigid body approach, it's hard. But TMT dynamics, as we called it at TUDEL back in 2010, it drives all of these vectors and matrices straight away for you, so it makes it easy to drive, understandable, and easy to manipulate if your system parameters changes. I improved that for the case of differential kinematics, and the beauty was you end up with a summation. So basically, the different elements you generate the derivations separately, and you just concatenate them in your final strip. You don't end up with a large Lagrangian that you have to go for the partial differentiation for the whole system and ugly equations. Inverse problem is easy then in any other rigid body dynamic case that you've already seen. And based on all of that theory, we provided a comparison between different methods. We know that lump systems are better for control. Constant curvature models are good for design. Modifying constant curvature model doesn't worth it. It doesn't improve the accuracy that much. Cutter is the most accurate but infinite number of states. What do you want to do with that when you design a controller? And shape function methods, learning methods, their robustness is limited to the richness of the data set. These are experimentally verified against our experiments with very soft robot against intensive external force. But then these are the simulations from the TMTDyn, and these are a comparison of this, different methods that I kind of talked about. The rigid body case, the Euler-Bernoulli with relative state, strains and torsion, the Euler-Bernoulli with absolute state, orientation and position of the state, and reduced order model. And we kind of observe, and you kind of see from the number of elements that if you go traditional rigid body dynamics, it's very complex to derive the equation. But if you go the finite element-like method or reduced order modeling method, you end up with either lower number of dimensions or faster generation of the equations. We found the finite element-like kinematics. It gives you the fastest derivations and simulations, but reduced order model gives you 1/3 or 1/4 of the number of states that you can play with if you're interested in designing a controller yourself. Since then, there has been a wave of new reduced order modeling techniques in the community for sensing, control. People did it for backbone estimation, for geometry deformation estimation, for shape, force estimation, etc. Also, we looked at the sensitivity of these methods and noted that if you go for absolute states and rigid body kinematics, the large equations tend to be more numerically unstable. So if you implement the cross-section deformation and change due to the braided actuators, you will lose accuracy, and at some point the simulations diverge. So I want to say go finite element modeling if you have a large system, go reduced order modeling if you want to do control. Okay. I tried different different cases with the TMTDyn, like a spider web, deformation of the a whisker, etc. But let's talk about more interesting things, implementing tendons, growing robots, and concentric tube robot dynamics in instability. Speaking of the concentric tube robot, this is how it looks in MATLAB when you use TMTDyn. If you read it, it is like human language. It is called a DSL or a kind of fluent interface. It's an object-oriented package, but then the way it is implemented that you can just follow implementing elements one after the other to make things easier. I followed the suggestion from a computer scientist to implement this, but noted that no one in the soft robotics community care about that. So people like their scripts and their user interfaces. But anyway, we have it, and we've improved it since. You see, we can capture the unstable snapping of concentric tube robots. We can capture hysteresis in the return motion. No one has done it before. You may say, okay, we didn't need it. That's why no one has done it. But anyway, I did it. And it kind of works. The results are really good. You see the experiments and simulation results are kind of matched. For the drawing robot, again, that's implementation. Okay, you may say it is a rod that's on, but no, we have actually captured the correct here. Going out of the material move, and we define terms like going from peak, going from base, etc., and implement it in the system. Again, simulation results are really promising, but it was a simple case. We're working on that. But what it looks, what is TMTDyn in compared to everything else? First, we were kind of the first. Well, after Grazioso's work on SimSoft 2019, we were kind of the first publishing our paper in 2020 at the same time as Pyelastica, and then there's a wave of software developed in 2021, 2022, mostly in the US. We use MATLAB. SoroSim uses MATLAB. Everyone else uses Python and C++, but the derivations will be transferred to C++, and I use the Sundial ODE, which is a very fast numerical solver in C to get real-time, near real-time performance in my simulations. But these are the possibilities, basically. But let me elaborate on that a bit, just quickly. We're trying to implement TMTDyn for control design with SOFA for interaction, but I want to argue that finite element model answers everything. Here we have a whisker, and we want to do train identification based on the vibration. Here you see hopefully you see the simulations in SOFA. Here you see the beam mechanics, and here you see the simulations in SolidWorks. There is no way that you can generate this surface plots of the design space if you go finite element approach. You know, it takes ages to generate all of these data points. So we need a theoretical approach, beam models, etc. still in the community. Finite element doesn't provide all the solutions. Also, implementing very complex things like growing robots and concentric tube robots is not an easy task. So I don't know why these are not playing. So we had, for the sake of time, I pass it, but we had implementation of concentric tube robot using Timoshenko beam in the SOFA, and also implementation of the eversion growing of growing robot in SOFA. And it takes this one cannot capture the snapping, and this one takes ages to grow, and you cannot basically do the design state space analysis for the design purposes. So that's my argument. We kind of need a balance, but we need SOFA for handling complex scenes, complex interactions, putting realistic objects in the environment. But when you're doing design, when you're doing new kind of soft continuum robots, and when you're doing control, you still need to stick to the beam model. And TMTDyn is actually a good software for that, because it provides you the means to do a comparison, to see an overall view of what's there and how it performs. The other stuff that we looked at based on the theoretical work that I did was variable stiffness structures and shape sensing through the embodiment, as you can see here, and also very complex but low-cost tendrils with as many joints as you have turns in this tendril. But okay, before I thank my collaborators, we have this Frontiers special issue. Just submit if you can, and this is the team of people that I work with for developing TMTDyn.
Cool. So let me know what you're thinking, Hadi, but we're already a little bit into the next talk. So would you want to punt questions to the panel, or?
Yeah, I'm okay. Sure.
Okay. Well, maybe if there are any questions while you get set up, next up will be Yu Wu, who's joining us from MATLAB, which is really exciting.